Welcome everybody to lecture 13, which is all over chapter 6.1, 6.4, and 6.6, I believe. They're just all about the idea of the derivative of the logarithm and the derivative of inverse trig functions, which really means they're just extensions of the last video, because all we're going to do is use implicit differentiation. Hint, hint, wink, wink, nod, nod. It's largely what this stuff is going to be about. Starting off, we're going to see a couple examples, and that's pretty much how this is going to work. But we're going to start off with this example here. We want to find dy dx given that y is equal to log base b of x. Yeah, I don't know. I don't actually have this memorized off the top of my head. But I do know that thanks to some algebra, we can rewrite this as b to the y is equal to x. And given that, we know that if we were to take the derivative of both sides, d dx of b to the y, d dx of x, well, let's rewrite this b to the y as e to the ln of b to the y. This is going to give us d dx of e to the y times the ln of b is equal to, well, d dx of x is just 1. That's convenient. Okay. Now let's stop and think about this for a second. That's going to need implicit differentiation, isn't it? Yeah, it is. Yeah, it is. Okay. So if it's going to need implicit differentiation, this means that what we're going to get out of it is going to be e to the y ln of b times d dx of y to the, or y times the ln of b. And again, all that's equal to 1. Well, by the constant multiple rule, we pull out that ln of b. And when we do all that, we're going to get that this is equal to the ln of b times e to the y times the ln of b times dy dx. All that's equal to 1. Okay, well, we can divide out all of this stuff to the left to isolate dy dx on its own. So let's do that really quick. We're going to have dy dx is equal to 1 over the ln of b times e to the y times ln of b, which we can rewrite as 1 over the ln of b times b to the y. But hey, b to the y, we just said was x. So that means then dy dx is equal to 1 over the ln of b times x. And that, ladies and gents, is what the derivative of log base b of x is. That is to say that, let me rewrite all of this. Let me write it down here actually. That is to say that dx of log base b of x is equal to 1 over the ln of b times x. That's it. But notice what else this means. If we were to base e, so if we were to take the ln of x instead of log base e, we're using log base e, which is the same thing as the ln. Well, the ln of e is just 1. So this automatically tells us that dx of the ln of x is equal to 1 over x. Now I challenge you to check something out. What is the ln of negative x? What does that come out to be? I want you all to take the time to find that out on your own. Having said that, I'm going to keep moving on. Now for this next example, we're going to find dy dx given that y is equal to sine inverse of x. Having said that, I should note about some language here and some notation. I generally call this the arc sine, and we'll write it as arc sine of x, as opposed to sine inverse, just because I like that notation more. But given that y is equal to the arc sine of x, we have then that x must be equal to the sine of y, given that y is between negative pi over 2 and pi over 2. We'll take a couple minutes to think about why that is. Why does y have to be between those values? All right, having given y'all some time to think about it, I'm going to keep moving on a little bit. And notice, since we've got x is equal to sine of y, we can apply implicit differentiation of that, right? So applying d dx to x equal to sine of y, we get that the left-hand side is pretty obvious. It's just 1, right? Yeah. That's what we keep doing. So of course that's 1. Nothing changes there. Here, we look at it and we say, chain rule? Yes, that's absolutely right. Chain rule is what you need to apply here. Sine is your outside function, right? And y is your inside function. So this thing's going to come out to be cosine of y times dy dx. Okay. Now what? Well, now we need to isolate dy dx from everything else. Okay. It means we need to divide both sides by cosine of y. Let's do that. Right? It's going to give us 1 divided by the cosine of y is equal to dy dx. Well, hey, wait a minute. Can we rewrite cosine of y in terms of sine of y? Yeah, we could use the Pythagorean theorem, right? Since, oh shit, it went the chop. Got it. Awesome. All right. Since cosine squared of, I'm going to write t, plus sine squared of t is equal to 1, we can rewrite this as 1 divided by the square root of 1 minus sine of y. My mistake. The square root of the quantity 1 minus sine squared of y. And all of that is equal to dy dx. Let's take a minute here, look at what's going on. At any point, is this going to give us a value that doesn't exist? Do we need to worry about anything here? No, not really. Everything seems to be working out, right? Cool. We've got where y exists. Everything looks good. But didn't we say a minute ago that sine of y was equal to x? So couldn't we write this a little bit more cleanly to be 1 over the square root of 1 minus x squared is equal to dy dx? And in fact, we could. We could absolutely write that. To get that, d dx of the arc sine of x is equal to 1 over the square root of 1 minus x squared. Where x sits between -1 and 1. Cool. So, having said that, I'm going to leave cosine up to y'all now. Because I do want y'all to do these and play with these and use these on your own. I do want y'all to get that sort of practice in. But really, this is how you're going to find all of your inverse trig functions. That's really all that this section 6.1, 6.4, and 6.6 are about. It's just saying, okay, how can I rewrite one of these functions as an inverse? Just saw it with sine. And I'll let y'all do it with cosine. And then how are we going to use that inverse in implicit differentiation to find out what the derivative of that original equation was? So, starting off with these inverse functions, we're going to rewrite them in terms of their inverses, and then apply implicit differentiation. As per usual, if y'all have any questions, by all means, please drop me an email. This lecture was quick and short and dirty, so it's okay if you have questions. I totally get it. I just went over 2 examples and said, there you go! There's really the need to show these examples was really what I thought that these 3 sections, 3 bits need. But if you do need more help with it, by all means, please drop me a line, send me an email. I'll be posting office hours. Yes, this is the same day as that other lecture. But yeah, have a good one, everybody. See y'all next time.